Imagine you have a factory, and for that factory, you have bought a 200 kVA transformer, induction motors, and conductors to carry the current. But after a few months, you notice that your transformer is not delivering the power that it should be. Your induction motors are drawing more power from the utility, your conductors are overheating, and your electricity bill is skyrocketing. Yeah, sounds like a lot of problems, right? And the problem or the cause of that problem could be the low power factor, right? In this video, we are going to talk about how this power factor can be problematic for you and how you can improvise it by understanding its basic principle and different common ways that is used to improve the power factor. Now, in the previous video, we discussed about the basics, the very basics of power factor, what is power factor and the things related to that. On that video, a lot of you commented that you wanted to have a video, a dedicated video in which we'll talk about the ways to improve the power factor. And based on your comment, here is the dedicated video on that particular topic. So we'll go and understand how we can improve the power factor in a couple of minutes. But before that, if you find the videos helpful, then do like the video and do subscribe to the channel so that you get notified about all the videos that are coming on the channel. All right, so let us continue with the factory example that we were discussing initially. So we have a factory, and for that factory, I bought a 200 kVA transformer, and I'm hopeful that this transformer will give me at least 170 kilowatt of power for my working. Similarly, in the factory, I also have induction motor. Let's say 1 HP is the rating. And based on the calculation that I noticed, the normal current that will flow in the factory would be 280 ampere. And based on that, I selected the conductor which are suitable to carry 300 amps continuously without any problem. Right now, this is my primary calculation. But as the production started, the months passed, and when I received the electricity bill, I was surprised. None of my machines were working efficiently the way I had expected them to. My transformer is not giving me 170 kilowatt. My induction motors are drawing huge power, and the cables are overheating. The reason is the poor power factor. And because of the poor factor, the utility also penalizing me for maintaining that. And for that very reason, my electricity bill is also very, very high. Now, this poor power factor creates a lot of problem. Let us quickly understand what are the things that is happening with the transformer, motors, and conductors with poor power factor. So first, the transformer. The very purpose of the transformer, why I bought is because I wanted to have at least 170 kilowatt of power. That's why I bought 200 kVA transformer. But since my power factor is poor, the transformer is only able to deliver 140 kilowatt of power. So I'm still short of 30 kilowatt. So definitely my transformer is not working efficiently. The reason, poor power factor. And since it's not meeting the requirement that I have 100% of that, either I'll have to purchase, higher rating transformer if I maintain the same power factor throughout the lifetime. So I may have to purchase a 250 kVA transformer. So that is going to put additional load on my pocket, right? Because I have to invest into the new transformer, and transformer is not a cheap device. A lot of money needs to be invested to buy the transformer. So this is a problem. Let's see what is happening with induction motor. Now, induction motor, we bought it in the assumption that it is 1 HP motor, but our power factor is only 0.7. It is actually consuming 101.42 HP. So the additional amount that you see here is basically taken from the utility, and definitely utility is going to charge me for that extra amount. So again, there is load on my pocket. So this is also not good. My induction motors are also not working perfectly fine. Why? Because of the poor power factor. Thirdly, let us see what is happening with the conductors. Now the conductor I bought this, which is suitable for 300 ampere, because as per my calculation, the total current is 280 ampere. So 300 ampere I selected. But because the power factor is poor, the system is drawing 350 ampere continuous current. The question is whether this 300 ampere conductor will be able to carry 350 ampere continuously and safely. Of course, the answer is no. This additional current will start heating the conductor. You may not notice it immediately, but slowly it is degrading your conductor capacity. The insulation will weak down. It will also have a safety impact. So you may see that the insulation strength of your conductor is going down by 40 to 50% because of the poor power factor. And because the current is also increased, definitely if we assume the resistance of my system is 0.94, then the I square R losses has gone up as well, which is now 115 kilowatt. So this is purely the power loss I'm doing, no useful work. And everything is happening because we have poor power factor. So certainly it is very much clear that we must maintain good amount of power, not only to make sure that our machines are working efficiently, but also to make sure that we don't have the financial losses, right? So it's very critical that we maintain the good power factor. So we saw that with the help of, since our power factor is 0.7, everything is poor. Now let's see what happens if we improve the power factor from 0.7 to 0.9. First, let's start with the transformer. So here you can see with 0.7 power factor, the power delivered was only 140 kilowatt. But if we improvise to 0.9, that the same transformer will be able to deliver 180 kilowatts. Significant amount of improvement there. And maybe I can, utilize the transformer in a better way if we have better power factor. Same thing about my induction motor. With 0.7 power factor, it was becoming 1.42 HP, but since I made it 0.9, it has come back to 1.1 HP. So again, significant amount of reduction, and this will help me to save my electricity bill, save the excess amount of power that I am consuming. And also the same thing with the conductors. With 0.7, the current was 350 ampere and the I square R losses were around 115 kilowatt. If you improvise it to 0.9, it goes to 280 ampere. So significant reduction in the current. And as a result, the I square R losses has also dropped down significantly. It is now 69.54 kilowatt. That's a significant amount of reduction. And all of this is happening because we improvised the power factor. So certainly improving the power factor is not a choice, but it must do things if you want to make sure your machines are working fine and your electricity bill stays in the control. But now the question is, how can we improvise the power factor? Let's understand that in the next chapter. So here, let us first understand the very basic principle, the basic fundamentals of how we can improve power factor. Let us understand that with a simple analogy. Imagine you have number 0 with you and you always want to keep that number as 0, but somebody added plus 7 to that. Now the resultant number that you have is positive 7, but that's not what you want. You want to have 0 back. So what you can do? Of course, you can add the opposite and the exact same number to that. So that means we'll add a negative 7 and that will give us back our 0 value. And that's what we wanted. Well, if you understood this simple mathematics, you have understood how we can improvise the power factor of the system or the power factor of the circuit. The only thing is I need to explain it to you in the technical terms so that you understand it in the better way. Now, the basic thing that you have to understand is that the problem of poor power factor is arriving because you're consuming active apparent power and you're also consuming the active power, and both of this power are different. They are not equal. Imagine you're consuming 1000 volt ampere reactive apparent power, and out of that only 500 watts or 500 kilowatts is the active power. So your resultant power factor is very poor, 0.5, 0.6 in that range only. And that creates the problem. Your apparent power is not equal to your active power. Or in another way, the total impedance of your circuit is not equal to the total resistance of the circuit. Right? This is the very simple terminology that you have to remember. How to improve power factor? Make your total impedance of the circuit equal to the total resistance of the circuit. What does that mean? It means that there is no inductive element or there is no capacitive element present. The moment you took care of these two elements, your power factor will improve 100%. The moment we add them back into the system, one of them, then the problem of poor power factor will start. So what we have to do is we have to make sure that if we have inductive load and if we are drawing a lagging power factor is poor. So to tackle that, we can add the equal and opposite amount of capacitive reactive power. The moment we do that, our power factor will improve. Let us understand that with one simple example here. So here is the simple example that we have. We have 230 volt AC supply and we have 60 ohms resistance and 160 millihenry inductor in our system. Let's say this is a factory's parameter. Now, if you calculate the impedance of this circuit here, you will get the impedance as 78.2 ohms. And this is the very first problem. You see our resistance is 60 ohms, but the impedance is 78.25 ohms. So definitely the condition is not met for a better power factor, which was the system resistance equal to the system impedance. This is not the case. There is a difference. Your impedance is high. That means this factory will have poor power factor for sure. And with this, if you calculate the current will be 2.94 ampere almost. And with that, we can calculate the different power this circuit is consuming. And this is from this also, it is very evident that the power factor is poor. So you can see the apparent power consumed by this circuit is 671 volt ampere, whereas the active power consumed is 515 watts only. So both these powers are not same. For sure, the system will have poor power factor. And if you calculate that, it's gonna give you 0.768. That's the power factor of the system. Now I want you to understand the basics here. You see, the problem is getting because we have this inductor in the system. You cannot remove that 100% from the system because the most useful device, the induction motor, is basically the inductive load. And if you remove that, there will be a lot of problem because it's the very useful machine that we have. So we cannot ignore this, right? Now, but if we can remove it somehow, then what remains is 60 ohms resistance, and that will match with the impedance that we have in the system. So what we can do is we can add maybe equal and opposite amount of 160 millihenry or maybe 160 VAR apparent power. You can see we have, not apparent power, reactive power. You can see we have reactive power as 431 VAR. This is mostly the inductive in nature. If we add a capacitive power which is equal and opposite to this, then our apparent power will become equal to the active power. And in that scenario, we can say our power factor is unity. But that is the ideal scenario, and unity power factor is almost not possible. You can try to get near to that 0.96, 0.97, 0.98, but still you will have better results with that. So what is happening here? Let's understand from the power triangle. So we have active power here, we have apparent power here, and then we have the reactive power here. And the angle between these two is the power factor. This is what we understood in the previous video of power factor series. The problem is getting into the system is because of this reactive power that we have. Now, if we add equal and opposite amount of this, let's say we added a capacitor in parallel with our load, this reactive power will drop significantly. Let us say it is dropped to 231 VAR. And now you can see the apparent power is almost, it's not perfectly equal to the active power, but it's better than the previous scenario. And as a result, the power factor has improved, the current has gone down as well. So the basic principle of how to improve power factor is by producing equal and opposite amount of reactive power than what the circuit is consuming. And the different ways of improving power factor is basically the ways in which you can generate the reactive power in the system, the ways in which you can inject the reactive power in the system. In the next chapter, we will understand the three most commonly used ways of improving power factor. So we have three most commonly used ways of improving power factor. First, and the most commonly used, is capacitor or capacitor banks. It's also the most economical way of doing that. Second is a synchronous condenser, which is used for the heavy loads because these are expensive. And then we have phase advancers. Let us first start with the capacitor or capacitor banks. Now, most of the loads that you will see in the industry, they are inductive in nature. Example of that is transformer, induction motors, and other devices. So to avoid or to add the equal and opposite amount of reactive power, of course, we will have to have capacitors in the system, because inductor and capacitors are opposite in nature. If inductor is there, then we have to add the capacitor. You can say inductor is our +7 and capacitor is our -7. If you add them, they will cancel out each other and we will be back with our 0 value. Right. And that's why the capacitors are very widely and very popularly used for power factor correction. For example, induction motor, you have induction motor, you can add a capacitor in parallel to that and your power factor will improve, because whatever reactive power is needed by this induction motor is provided by this capacitor locally, and then as a result the induction motor will not draw that power from the utility. So you'll have a better utilization of induction motor. Also, the APFC panels, automatic power factor correction panels, are also used, which is nothing but a capacitor banks placed inside that, and there will be some logics provided in which it can automatically switch on and off the capacitor banks based on the load that is connected and based on the power factor that is there in the system. The next methodology is the synchronous condenser. Now, when we overexcite the synchronous motor at no load, it acts as a synchronous condenser and it is called as synchronous condenser. The condition is it must be on no load and it should be overexcited. Now, why is that? Let's understand. So here we have, let's say, synchronous motor, we have rotor and we have stator here. Now, to generate the required magnetomotive field, MMF, or the flux, there are two ways basically to do that. One, the stator will draw the power from the three-phase line and it will generate that for the motor. Or second, we add a DC exciter to the rotor and that rotor will generate that MMF for us. Or maybe the combination of both. Some power is taken by the rotor and some is taken by the stator. That is possible. Now, let's say we don't have DC exciter to our synchronous motor. So in that case, what will happen is the stator must consume the reactive power from the system to generate the required flux. So stator will consume that from our three-phase line, right? But if we excite the rotor with the help of a DC exciter, then the rotor will also provide some sort of flux to that, and the power that we are drawing from the three-phase line will reduce. And if we excite it furthermore, then the rotor will stand alone, will be able to supply the required flux to the synchronous motor, right? Now, if we go one step beyond, if we still add furthermore excitation to the rotor, then actually it will start delivering the reactive power to the system because we are over exciting the rotor. And in this situation, this machine is called as synchronous condenser. It will start delivering leading power to the system, leading reactive power, and which can be used to compensate the poor power factor caused by the inductive load, which is lagging in nature. And this in this scenario, this synchronous condenser basically acts like a capacitor, which is delivering the reactive power to the system. This is also widely used, but for heavy loads, heavy machineries, because this is expensive. The next is the phase advancer. Now, this is most commonly used for specifically for induction motors. So, what they are doing is they are connected to the motor and they are supplying the required reactive power to the motor locally itself for excitation so that it doesn't draw that power from the system. They act like just like the capacitor banks, but specifically used for the high capacity motors like more than 200 HP and more power induction motors. So those are the three common ways which are used for improving the power factor. Now let us quickly summarize what we have discussed so far. Poor power factor can reduce the machine efficiency, overheat the conductors, and increase the I square R losses. We discussed about this in the first chapter where we took the example of the factory. We did the actual calculations. Then improving the power factor is nothing but the injecting or producing the reactive power, right? And all the ways that we saw the capacitor bank, synchronous condenser, and phase advancers. They are basically helping us inject the required reactive power or produce the required reactive power locally, right? So I hope the concept of how to improve power factor and different ways of doing that is clear to you. If you found this video helpful, then do like this video and do share it with the people you think might be interested in knowing about the improvement of power factor. If you found this video helpful, do let me know that via comments, and do check out the description of this video as I've mentioned some of the videos and some of the resources that you should check out to learn more about the power factor. Thank you so much for watching, guys. I'll see you in my next one, but till then, keep watching, keep learning.